We are starting the fourth section of the quadratic unit today. You guys just had your mid-unit exam the other day. Hope you guys did well on that. And so today the focus is to learn about something called the complex number system. Before we get through that though, this lesson has two main objectives. It's to review how to work with radical expressions and then to learn about the complex number system and the imaginary numbers. So let's start off with Algebra 1 review of working with radicals. So your warm-up question I'm going to copy into your notebook as an example. So we're going to simplify the radical expression. Okay, this is all Algebra 1 review. To do this, you do have to be comfortable with your perfect squares, 1, 4, 9, 16, etc. Because on the warm-up, when you try to break apart a radical, you're trying to find the largest one of those perfect squares that goes into it. So 18 is not a very huge number. The largest perfect square that goes 18 is 9, and it goes into 18 2 times. So you're breaking apart radical 18 into radical 9 times radical 2 using something called the product property. From here, you take the square root of the perfect square to get 3 times radical 2, and 2 must stay inside the radical because the square root of 2 is a decimal. And when we're simplifying, we don't want decimal results. For some other examples we're going to do, so we're going to do 5 others reviewing these properties. Let's go ahead and try 6 others, radical 128 and radical 80. So take another minute, pause the video, see if you can go ahead and break those two down. I'm going to keep going. You would start off by finding that largest perfect square that goes into 128. I usually start off I like to divide that number by 2 and only test the perfect squares less than that. When you divide 128 by 2, you get 64, which just happens to be a perfect square. So that's going to be your winner. The reason why I'm dividing by 2 is because if it's larger than half of the number, there's no way it can be a factor. There's no sense in testing the perfect squares that are really close to 128. So we're going to break this into 64 times 2, which will become 8 radical 2. 80, if you divide 80 in half, you're going to get 40. So you could try 36, but 80 divided by 36 is a decimal. You could try 25. 80 divided by 25 is a decimal. You can try 16, and ding, 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 that is going to work. 16 is going to go into 85 times. The square root of 16 is 4, and you get 4 times radical 5. Please always write the perfect square factor first. Before I continue on, I did want to list the perfect squares. I normally do that first, but because it's almost 6:30 at night at the high school, I'm a little off right now. So perfect squares, these are the numbers that you're looking to see if they go into the number under the radical. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I'm going to do the first 16. Keep going with that list. We're going to have 121, 144, 169, 196, 225, and 256. These are the perfect squares you should become familiar with and should have memorized. You should be able to square root those numbers without a calculator, and they need to be in your brains. So the first 16 all the way up to 256, which is 16 times 16. Let's focus on some division examples now. So for example 4, if I give you the square root of 7 over 16, just like with the product property, the quotient property allows you to separate these. So you're going to get radical 7 over radical 16. 7 is not a perfect square, and no perfect squares besides 1 go into it evenly, so 7 must stay inside the radical, but the square root of 16 is 4. That is finished. Next example, radical 15 over 2. Break it apart again. Give them each their own radical. 15, again, not a perfect square. No perfect squares go into it. And same with 2. But you're not allowed to keep a radical in the denominator. It's not considered simplified. So what you would have to do is do something called rationalizing the denominator, where you multiply the numerator and denominator by the denominator. So this is called rationalizing the denominator. In the numerator, because the 15 and the 2 are both under a radical, you're allowed to multiply them together to get 30. And in the bottom, radical 2 times radical 2 is radical 4, which is just 2. That's the whole reason you do it. When you multiply a radical by itself, you're just going to be left with a number underneath called the radicand. The radicals end up canceling out. You cannot divide 30 by 2 because the 30 is under a radical and the 2 is not, so that has to stay the way it is. You could just double check radical 30 though to see if any of our perfect squares up here go into 30, but 1, 4, 9, 16, 25, they don't go into 30. Well, 1 does, but one goes into everything. So that's it on that one. We have 2 more examples, and then we're going to move on to the complex numbers on a note-taking guide. So 6 times 25 thirds, radical 25 thirds. Break it apart. Also going to throw the 6 over 1. That'll help me because the rest of the problem's a fraction. Before I rationalize here to get rid of the radical 3 in the denominator, I want to take the square root of 25. That's a perfect square. I don't want to ruin that number by multiplying by radical 3. So let's do that first. This is going to become 6 over 1 times 5 over radical 3. I'm going to bring this into one fraction. 6 times 5 is 30, and then 1 radical 3 is just radical 3. Cannot divide those because 1's under a radical, 1 is not. Announcement at like 6:30 at night. So pause for that announcement. Sorry, guys. Okay. Let's get rid of the radical. We're going to rationalize. In the numerator, the 30 is not under the radical. 3 is, so you can't multiply them. You're going to just leave it as 30 times radical 3. And in the denominator, radical 3 times radical 3 is radical 9, which is just 3. There is one last step to this problem. The 30 divided by 3, you can do that because they're not under radicals to get 10 radical 3. So the product and quotient property allow you to separate radicals or bring radicals together when they're being multiplied or divided. Let's try one last multiplication. So 3 radical 12 times radical 6. Now right now 12 and 6 are neither of those are perfect squares. So what you would do first in this example is bring them together under one radical by multiplication, and then try to break that one radical apart by finding a perfect square factor. So you're going to look at your list of perfect squares and find the largest one that goes into 72. I'm going to pause while you guys find that and then check to see your answer. It's going to be 36, and it goes in 2 times. This will become 3 times 6 radical 2, because that 3 was being multiplied by the radical. And then you're going to get 18 radical 2. These properties do not work with adding and subtracting radicals. Think of addition and subtraction of radicals like terms. You can't combine x's and y's. Therefore, you can't combine radical 2's with radical 5's. They have to be like radicals in order to be able to add them. So what I mean by that, if I did give you 2 radical 5 plus 9 radical 5, that would equal 11 radical 5. I can add them because they're considered like terms. If that was a radical 5 and a radical 3, you would not be able to add them. The only way to combine them is if you change them to their decimal form and then added, which we're not doing right now. So they have to be like radicals for addition and subtraction to work. Unlike with multiplication and division, they don't have to be the same radical. So from here, we're going to go over a note-taking packet. So we're switching gears a little bit to learn about complex numbers. So you guys are getting this packet, and we're working on this today and then also tomorrow. So today our goal is just to get through this first page, and then the rest of it will be tomorrow's lesson. It's all going to be in this one video, though. I'm not going to separate the videos. I'm just going to keep teaching through it. So this is a day 1 and a day 2 video. So let's start about talking about complex numbers. If we read through the top part here, it says, not all quadratic equations have real number solutions, which we've learned about. We think about roots. Not all functions have 2 roots. They don't necessarily have to touch the x-axis. If we look at the equations, for instance, if I give you x squared minus 1, I'm just going to rewrite that down here. X squared equals -1. That'll have no real number solution because when you square a number, it never comes out negative. You just think about this. When you square this x value, there is no way it can come out to be a negative answer. So when you attempt to solve for x by square rooting both sides, which you'll learn more about next section, you're going to get x equals and then a negative under a square root. That we have talked about back in September when we did domain restrictions and how certain numbers couldn't be subbed in for x because they gave you a negative radicand. Can't square root a negative. Okay, there's no real solution to that. If you think graphically, a problem that has no real solutions, no real roots, it can't cross the x-axis. So why don't you take a second, I'm going to pause the video and see if you can find and draw a graph where it won't ever touch the x-axis. You could draw something like this. Shifted up opens up, or shifted down opens down. Something to that effect. Won't have any real solutions. But what they will have are 2 imaginary solutions, which are part of the complex number system. So to overcome this problem, mathematicians created an expanded system of numbers using the imaginary number I. You'll see an italicized I. That's the imaginary unit. And it is defined as, please put a circle or a cloud or a square or a box or something around this fact. I is equal to the square root of -1. So anytime you have a negative underneath a radical, your answer is going to have an I involved. So let's try to simplify these radicals like we just did in our notebooks, but with negatives. Okay, I'm going to scroll down here. So the square root of -9. You don't have to write this every time, but I do want to show you where it's going to come from. I could rewrite this as the square root of 9 times the square root of -1, essentially pulling the negative out. The square root of 9 is 3, and by definition, the square root of -1 is I, so it becomes 3i. I'm going to do one more with you, and then I want you to try the other 3 on your own. If we just skip over to the square root of -27, I again could break that into the square root of 27 times the square root of -1, and then break down the radical 27 like we were just doing. So I would break that into radical 9 times radical 3, because 9 is the largest perfect square that goes into 27, which would give you 3 radical 3. And the square root of -1 is an I. The order that you will see this written in, and technically you could write it in any order because multiplication is commutative. 2 times 3 is the same as 3 times 2. But the way you'll normally see it in is the whole number, then the I, then the radical. So square root of 9 is 3. I'm going to sneak in that I in the middle. And then this radical 3, which stays inside, will be written last. So that is the order. Now, as you saw in those 2 examples, I separated the square root of -1. You don't have to do that every time. All you really need to know is that anytime you see a negative under the radical, it's going to come out of the radical as an I, as part of your answer. So you can skip that step and just write I with your answer anytime you have a square root of a negative. So pause the video, try the other three on your own. For the one I skipped right here, negative is going to come out as I, and the square root of 16 is 4. So 4I is the correct answer. Next one, we have 245. Negative is going to come out as I, and we have to break apart 245 and divide it until we find the largest perfect square that goes in. And that's going to be 49, and it goes in 5 times. Don't forget about that I. Square root of 49 is 7. Then we write the I, and then we write the radical 5. And last but not least, square root of negative 5. 5 is not a perfect square, and there are no perfect squares other than 1 that go into it, so the 5 is stuck inside. The only thing you can do on this last one is just take out the I and leave the 5 underneath the radical. That's pretty much it in terms of simplifying with I. We're going to move on to just talking about where this I fits in the idea of the complex number system. So let's read this little paragraph, and this is where we'll stop for today. An imaginary number that is written in standard form, and this is standard form different than a quadratic, so we're not referring to ax squared plus bx plus c. I'm talking about the standard form of a complex number, which follows the format a plus bi, where a and b are real numbers like we're used to. The a is the real part of the complex number, and the bi is the imaginary part. If the b value is not equal to 0, then a plus bi is considered an imaginary number. Okay, so a plus, anything you see with an I in it is considered an imaginary number, part of this complex number system. If a equals 0, so imagine covering up the a, and all you're left with is bi, then that would be considered a pure imaginary number. So we're going to look at this Venn diagram to show the relationship between numbers. So complex numbers is the hierarchy, the largest category of everything. And within complex numbers, we have real numbers that we're used to, and the imaginary numbers that we're now learning about. Real numbers are everything: decimals, fractions, integers, 0, positives, negatives, square roots, cube roots. Those are all real numbers. Okay, so 3 is a real number. Negative 2 is a real number. 0.7 is a real number. Negative 3/4 is a real number. The square root of 5 is a real number. Those are all real numbers, just to throw some examples there. And you can break down real numbers even further into rational numbers and irrational. Rational has the word ratio in it. Ratio means fraction. You can write it as a fraction. So any number that you could write as a fraction is considered rational. Like 1/3. Okay, even the number, whole number 6, because you could write it as 6/1. Those are rational numbers. Even repeating decimals like 0.666666666 repeating, that's a real number or a rational number because you could write that as 2/3. 0.2 is a rational number. Okay, 0.2 can be written as 2/10, which simplifies to 1/5. We go down further. Integers are positive, negative, and 0 whole numbers. Positive, negative, 0 whole numbers. Those are the numbers that you'll see on my number line in my classroom. So meaning no fractions, no decimals allowed. But they can be positive, they can be negative, and it can be 0. And then whole numbers are non-negative integers. So basically you're just excluding the negative numbers. So 0 and above, but still no decimals or fractions. And then down here, irrational is the opposite of rational. So those are numbers you are not able to write as a fraction. Most common one that people know is pi, 3.14. So that decimal just keeps going and going and going and going and going and going and going, and you cannot write it as a fraction. The square root of 2, you get the square root of 2, which is 1.41, that also is not able to be written in fraction form. Those are examples of irrational numbers. With the imaginary number system, following that idea of a plus bi, so 5 plus 7i, that's an imaginary number, the a plus bi format. And if it was a pure imaginary number, you wouldn't have the 5, you would just have the 7i. So those are just examples of the complex number system. The new part that we're focusing on is the imaginary part. So at this point, we're going to end for today. In terms of the homework in this packet, you could start it tonight, but you haven't learned everything yet. Tomorrow, we're going to finish up and focusing on adding, subtracting, multiplying, and dividing these imaginary numbers. So around 20.5 minutes, day 1 is over, and I'm going to go ahead and continue on with day 2's notes. So for day 2, like I just said, we're going to go ahead and perform other operations. So add, subtract, multiply, and divide is our goal. And then you should also have some class time today to continue working on your homework. So for number 1, focus on the sign between the imaginary numbers. This is an addition problem. For adding, you're just going to drop all parentheses and combine like terms. You're going to combine the real parts and the imaginary parts together. 4 plus 3 is 7. Negative I plus 2i is positive 1i. That's done. If you look at the directions, it does say we want the answers in standard form. That's in the a plus bi format. So the real part, then the imaginary. Make sure you're paying attention to that plus sign in the middle. A lot of students will try to distribute this out and multiply them when it's not a multiplication example. If we look at number 2, it's subtraction. Subtracting a little harder, just like we did in September. Subtracting more than one term, you need to distribute the negative to the second imaginary number. So we're going to get 7 minus 5i minus 1 plus 5i. And then go ahead and combine like terms. 7 minus 1 is 6, and the negative 5i plus 5i cancel. So when we subtracted those, we ended up with a real number answer. It's no longer imaginary. And the last one is a combination of addition and subtraction. We're going to go from left to right. The 6 is just going to come down. We're distributing a negative 1 here. So it's going to become plus 2 minus 9i. And then you're distributing a positive 1. Positive 1 doesn't really change anything. Positive 1 times negative 8 is just negative 8. So instead of writing plus or minus, I'm just going to write minus. And positive 1 times positive 4i stays positive 4i. Combine all my like terms. 6 plus 2 is 8. Minus 8, those end up canceling. And negative 9i plus 4i is negative 5i. That's a pure imaginary. So if you look at our answers, I had an imaginary for the first one, real for the second, and a pure imaginary for the last. I'm going to scroll down and move on to multiplication. There's one new fact that we need to know when it comes to multiplying. So we're going to take the definition of the imaginary number, which was I equals the square root of negative 1, and we're going to square both sides. So I'm just going to rewrite it down here. It's going to give us another fact that we're about to use. So I'm going to square the left, square the right. That's going to give us I squared equals the right side. Squaring and square rooting are inverse operations, so they cancel, and you're just left with negative 1. So this is another fact that's very important. The fact that I squared is going to equal negative 1. Notice in standard form, a plus bi, there is no I squared. So anytime you have an I squared in your answer, you're going to need to replace it with negative 1. That's going to come up with the multiplication and the division. So let's go ahead and work through these multiplication problems by distributing. Number 1, distribute the 5i. You're going to get negative 10i plus 5i squared. As we just learned, I squared is negative 1, so we're going to replace that and multiply. 5 times negative 1 is negative 5, and that should be written first, and then the minus 10i, because you're in the format of a plus bi, real part, then imaginary. Okay, I'm going to do another one with you, and you guys are going to practice a couple on your own. So 7 times negative 1 is negative 7. We're just distributing these all out. 7 times 2i is 14i. Negative 4i times negative 1 is positive 4i. And negative 4i times 2i is negative 8i squared. I'm going to do 2 steps at once. I'm going to combine my middle terms and replace the I squared with negative 1. This is usually one of the top questions students get wrong on the post-test because they leave I squared as I squared and don't replace it with negative 1. This is a very common mistake problem for students. Also, sometimes students just don't write I times I is I squared. I times I is I squared. So plus 18i minus 8 times negative 1. Then I'm going to get a positive 8 at the end, which I'm going to combine with my negative 7 to get 1 plus 18i. Number 3, before we distribute, I would like you guys to write down a word next to this because it's going to come up in the division example. Those are considered conjugates of one another, and that's because the factors of the imaginary numbers are identical except for one is plus and one is minus. Something special is going to happen when you distribute these out. I'm going to get 36 minus 18i plus 18i minus 9i squared when we distribute. The middle terms cancel. That will happen 100% of the time when you multiply an imaginary number by its conjugate. The middle terms will cancel. So you could technically skip the step of multiplying the outer and the inner and just multiply the first and the last term. This will become 36 minus 9 times negative 1, 36 plus 9, which is 45. Okay. I'm going to have you guys try number 4 and 5 on your own, and then we'll come back and do number 6 together. So you guys can pause, try the next 2, and then check. Got to be careful on number 4. When you're squaring and there's addition and subtraction, you cannot distribute the square. You got to go ahead and write this problem twice. So I will get 25 minus 45i minus another 45i plus 81i squared. These are not conjugates. The middle terms do not cancel. They have the same sign, not opposite signs. So 25 minus 90i plus 81 times negative 1. So that's going to become 25 minus 90i minus 81. And if we do 25 minus 81, we're going to get negative 56 minus 90i. Moving on to number 5. Distributing the negative 6 and combining like terms. Make sure you write the real part first and then the imaginary part. That one was nice and easy. And the last one on the multiplication, if you look at number 6, the first one is not being multiplied by the other two, so I'm just going to drop the parentheses and bring it down. And then it's addition, so I don't really have to worry about my signs. I'm going to go ahead and just distribute out the other two and continue my row. So negative 6 times 11 is going to be negative 66 plus 6i plus 11i minus I squared. Combine my like terms and change I squared to negative 1. 1 minus 66 is negative 65. If I combine the negative 4i with the 6i with the 11i, I'm going to get 13i. And then I'm minusing I squared, so I'm minusing negative 1. When you minus a negative 1, it turns into adding 1, and I will get negative 64 plus 13i. I did forget the I right there. And that's it on multiplication. So you're just distributing, but you have to make sure you replace the I squared with negative 1 at the end. Last skill is dividing. Okay. Before that, though, it's going to involve the idea of a conjugate. So this is just defining what a conjugate is. So it says in example number 3 in the previous problem, those were conjugates because the two factors were of the form a plus bi and a minus bi. So same except for the sign. When you multiply to find the product, it's always going to come out to be a real number answer. We want to use this fact to help us do division. It's going to come up. So we're going to skip number 7. You could, actually, let's not skip it. Let's do it. So come up with another example, and it's conjugate, and then multiply them out. So pause, try on your own, and then look at mine. I'm going to do 3 plus 7i and 3 minus 7i. Because they're conjugates, the outer and the inner will cancel. So I'm just going to do 3 times 3, which is 9, and 7i times negative 7i, which is negative 49i squared. I squared is negative 1 times negative 49, so it's going to become plus 49. And when I add those together, I will get 58. So I get a real answer, not an imaginary. So let's do the division. So think of when we did rationalizing the denominator, how I didn't want a radical in the denominator. Well, with imaginary numbers, we got to get these into a plus bi format, which does not have any imaginaries in the denominator. We got to get rid of it. So to get rid of the imaginary in the denominator and make it a real number, we multiply by the conjugate, because that'll give me a real number. So I'm going to throw parentheses around this because we're going to be multiplying. And we're going to multiply by the conjugate of just the denominator. So if the denominator is 1 minus 2i, we're going to multiply top and bottom by 1 plus 2i. You're allowed to do that because as long as you do it to both, because it's really like multiplying by 1. When you multiply by 1, you're not changing the meaning of the problem. In the top, they are not conjugates, so you have to distribute it all out. So you're going to get 5 plus 10i plus 3i plus 6i squared. In the bottom, they are conjugates, so you can just do the first and the last. 1 times 1 is 1. Negative 2i times positive 2i is negative 4i squared. And then I'm going to keep simplifying the top and the bottom. The top, I'm going to get 5 plus 13i. This is really negative 1. And 6 times negative 1 is negative 6. In the bottom, this is negative 4 times negative 1, which will become plus 4. Negative 4 times negative 1 is positive 4. I will then get negative 1 plus 13i over 5. To get it in the a plus bi format, you just divide by 5 individually. So we will separate this as negative 1/5 plus 13/5 I. And that's all there is to that. So your key thing with division is you have to multiply by the conjugate of the denominator to go ahead and figure out that. Let's try number 2. What would be our conjugate that we multiply by? Think about that for a minute. Hit pause. And it's going to be 4 minus 6i. In the numerator, we're going to get 12 minus 18i plus 8i minus 12i squared. And in the bottom, we're going to get 16 minus 36i squared, because the middle terms will cancel out. You could do it. If you don't remember it, the middle terms cancel out. You can distribute it all the way out. I'm just trying to save you guys a step. Remember that I squared become negative 1. So in the top, we're going to have 12 minus 10i, and then negative 12 times negative 1 is positive 12, over 16, and then negative 36 times negative 1 is positive 36. So I will get 24 minus 10i over, and that's going to give me 36, 46, 52. Separate them. And this time, though, when you separate them, these fractions can be simplified. So I'm going to divide the first fraction both by 4. So when I do that, I'm going to get 6 over 13. And then the second fraction, I can divide both by 2. And I will get 5 over 26i. So at the very end, I could simplify those. And that is it. So whatever time there is left in class today, you guys can work on the homework. And tomorrow will be a practice type 3 that includes SAT work on this skill. And then we'll move on to solving quadratics, which is probably the longest section of the quadratic unit. And it'll bring a lot of ideas that we've been talking about throughout the unit together. So tomorrow, type 3, and then you're going to learn how to solve.